of the Galerkin weighted residual technique. So we know that we have mainly four type of weighted residual method. One is the Galerkin residual method, Galerkin weighted residual method, least square method, point of collocation method, and subdomain method, that also known as subdomain collocation method. So in that Galerkin weighted residual method, what we observe that we assume that weight function same as our trial function, and we try to minimize the error in an average sense over the entire domain and try to get our solution. In the least square method, what happened? We basically try to find the square of the error and we minimize the square of the error with respect to unknown coefficient. Here you just see the term is the least square. Okay, so basically what we will do, we'll find the square of the error and we try to minimize, we try to find the least error. Okay, we try to minimize the error with respect to unknown coefficient. Okay, we try to minimize the error with respect to unknown coefficient. So how to minimize? We will take the derivative of the square of the error and we will make it 0. So here you just see, if we know the error, then we will find the square of the error and we try to minimize the error, square of the error with respect to unknown coefficient. So what we will do, how we'll minimize, we'll take the first derivative and we'll make it 0. Okay, so for example, if we have a unknown coefficient, we don't know what the coefficient we have till now. So for example, we assume that we have an unknown coefficient, that is Ci or C1, C2, C3, like that. Okay, so you will take the derivative of the square of the error and we'll make it 0. If we do the derivative, so what we'll get? We'll get 2 here. Okay, we will take the derivative of this square. So we will 2r delta r by delta c. Okay, that will be equal to 0. Now again, if we take 2 in the right hand side, obviously it will be 0. So we will have r del x delta r by delta c. Okay, delta c, that will be 0. Now here you just see this is very equivalent to our residual method, where weight function we assume as the first derivative of the error. Okay, so here weight function is the first derivative of the error with respect to the unknown coefficient. Okay, so once we find that first derivative of the error with respect to unknown coefficient, and if we integrate, okay, if you operate over the error and integrate over it and try to make it 0, then we'll make it 0 and we'll try to find our unknown coefficient. Okay, so here you just see that our weighted residual method is that we have weight function and we operate on the r and we try to make the 0. Okay, we try to make the error 0 in an average sense over the entire domain. So here our weight function is the first derivative of the error with respect to unknown coefficient. Okay, so this is basically least square method, where we find the square of the error and try to minimize the square of the error with respect to unknown coefficient, and we make that derivative of the square of the error that equal to 0, derivative of the square of the error with respect to the unknown coefficient equal to 0. And once we do that, what we'll get, we'll obtain that our weight function is the first derivative of the error. Okay, once you obtain the weight functions, and again this is similar to our Galerkin method, we'll have weight function that operating on R and we're making it 0 in an average sense over the entire domain, and we'll get it 0. So we'll basically try to find our unknown coefficient. Here again, you just see we have simply supported beam, and simply supported beam means we have x is equal to 0 and y is equal to 0, y is equal to 0 at x equal to 0, again y is equal to 0 at x is equal to L, and we have moment is acting there, and for this case we have our exact solution like this. Okay, and since moment is acting there, so our moment equation will be EI d2y dx2 d2y dx2 minus m0 That will be 0 if y is our exact solution. Okay. Now here, what we do? We will assume one trial solution, one approximate solution, and what we will do? We'll put the value into this equation. We'll put the value into the equation. Again, the trial solution basically should satisfy our boundary condition. Here, our trial solution is here a sin pi x by L. So, trial solution must satisfy our boundary conditions that our actual solution is satisfying. So, here our actual solution is satisfying this boundary condition, basically 0, vertical displacement is 0 at x equal to 0, and vertical displacement is 0 at x equal to L. So, that u trial function also must satisfy the same boundary conditions. Here also you can see if x is equal to 0, u is equal to 0, and at x is equal to L, u also is coming 0. Basically, it is satisfying the same boundary condition. Okay, so now we'll have the trial function. Okay, and we'll try to obtain our moment equations ei dt u dx2 minus m. Again, that will not be 0. If u is equal to y, then time this equation will be 0. If u is not y, then we'll have some error. So what happened here? We get that our error. We'll get the error. So we'll get the error like this. Get the error like this. We'll get the error like this. Okay. So how we're getting it? We are basically making ei d2u dx2 minus m0, that is equal to our error. Okay. Now already we have discussed that in the weighted residual method, what we'll do? We'll take the first derivative of the error. Okay, with respect to the unknown coefficient. With respect to unknown coefficients, what coefficient do we have? The coefficient is the here a. So we'll take the derivative of error with respect to a. Okay, then we'll assign this is our weight function, and then what we'll do? We'll basically this will be our weight function, and this is our error. Weight function will operate with r, and we'll take the integration over it. We'll basically try to make the error 0 in the entire domain and in a average sense. Okay, so if you do that, we'll get this equation and we'll get the value of a. That value will come as a 4m0 L square by q by ei. Okay, so our approximate solution, our trial solution will be like this. Okay, so already we have discussed that our actual solution is coming like this. Our trial solution is in terms of sin pi x by L. Okay, so what we have to do now? What we have to do? You have to basically if you want to see how much error is there, you have to plot the data of y and of u. Okay, if you plot it, we get the graph like this. Okay, where this line is your actual solution and red line is your approximate solution. Okay, so see our actual solution is coming in terms of x L minus x, but our approximate solution we assume as a sin pi x by L. So we got our approximate solution in terms of sin, the trigonometric function. Since we assume a trigonometric function, so we also get. Okay, now since this value, okay, this value, if you see the nature of this x is different, so we need to plot it so that we can get some idea how much error is coming. So if you plot it, you will get this type of graph for both the curve. Here again, we have to assume some data of m, I, E, L, all the data you have to assume. If you assume the value in this way, you will graph like this. Okay, here you can see that our actual solution, okay, or you can say our approximate solution is very close to our actual solution. So it is acceptable. Our approximate solution is very close to our approximate solution. So this is the way basically we can solve problem using least square method. So let me summarize what we did in the least square method. The least square method, we first find the square of the error and we take the derivative of the square of the error with respect to unknown coefficient, and we basically assume this is our weight function. Okay, And in the same way we did for Glarkit method, we'll basically do the same thing. Del R by del A is basically unknown coefficient into the error. We'll try to integrate over the entire domain. We're making the zero in average sense for the entire domain. Once we do that, once we solve it, we'll get our unknown coefficient. Once we get the unknown coefficient, we'll get our trial solution like this. Okay. Once you get our trial solution or approximate solution, and we have to plot it so that you can see how much error is coming between our approximate solution and actual solution. So this is the way we should solve using square method. I hope you get some idea. Thank you.